Assalamualaikum. Hi everyone. So this is a video for chapter 5 hydrocarbons. In this video, we're going to discuss on the subtopic 5.1 alkenes, and at the end of this lesson, you should be able to first explain the following physical properties. We're going to discuss on the boiling point of, first, we're comparing alkenes based on its molecular weight, second, isomeric alkenes, and lastly, alkenes and cycloalkenes. And we're going to look also on the solubility of the alkanes in water and organic solvent. So now let's start. So we're going to talk first about the boiling point of alkane. Whenever we are talking about boiling point, it will always be related to our intermolecular forces. So in alkanes, what is the intermolecular force involved? Alkanes is a non-polar molecule, so the only intermolecular force that it will have is London forces, or to be general, we can also use van der Waals forces. There are three factors that can affect the boiling point of an alkane. The first one is the factor of molecular size. So the boiling point of alkanes increase as their molecular size increase. So the molecular size of an alkane is directly proportional to the number of carbon it has. The higher the number of carbon, the bigger the molecular size. Why? So bigger molecule will have a larger surface area, and when the surface area is larger, more van der Waals forces can be formed between molecules. Thus, the van der Waals forces exist between molecules becomes stronger, and more energy will be needed to overcome the stronger van der Waals forces. So like I mentioned just now, in our alkane, since it's a non-polar molecule, so the only intermolecular force that it will have is van der Waals forces. To be specific, it's London forces. So these forces will be affected by the molecular size, directly proportional to the surface area of the molecule, the surface area where the attractive force of the van der Waals forces occur between the alkanes molecules. Let's look at one example, the comparison between the boiling point of methane and butane. So, methane, a 1-carbon alkane, and butane, a 4-carbon alkane. So, this is a methane, CH4, 1 carbon, the boiling point is negative 161 degrees Celsius, while for butane, CH3, CH2, CH2, CH3, a 4-carbon alkane. So the boiling point is negative 1 degree Celsius. Now, if you look at the structure, over here, clearly we can see that the size of methane is much more smaller than the size of butane. Besides looking at the actual molecule here, we can also compare the size by calculating its molecular weight or its molecular mass. So for methane it's CH4, so the molecular mass of methane will be 16 gram per mole. So let me just write it down here, 16 gram per mole. And the molecular mass of butane will be 58 gram per mole. So there is a significant difference between its molar mass. So as the molar mass increase, the molecular size of the alkanes will also increase. So the van der Waals forces between the molecules will increase as the surface area increases. So if you look at the butane over here, the surface for the van der Waals forces to occur is larger compared to the one in our methane. So the explanation over here. So butane has bigger molecular size and larger surface area than methane. So that's why stronger van der Waals forces exist between butane and molecule. So more energy is needed to overcome the forces. Therefore, it has higher boiling point than methane. So the boiling point of butane is higher than the boiling point of methane. So if you were to answer a question about comparison between two alkanes, so you will do it like this. The second factor that can affect the boiling point of alkane is branching, the effect of branching. So, effect of branching will only occur in isomeric alkanes. So, for isomeric alkanes, the presence of branching lowers the boiling point if the number of carbon are the same. So, in other words, for effect of branching in alkanes to take place, so the alkane itself, it must have number of carbon that is the same. Okay, meaning, in other words, when we talk about isomeric alkanes over here, we are actually talking about our chain isomer. Still remember your chain isomer? It's when we introduce a chain, we shorten or we longer the parent chain. Okay, but the molecular formula of the alkanes are the same. Okay, so why does branching affect the boiling point? So, branching will reduce the surface area and the molecule will become more compact. Okay, first we have a very long chain and then we start reducing the parent chain and then introduce branching. So what happened? The surface area of the molecule will decrease. When the surface area is reduced, less van der Waals forces can be formed between the molecules. Thus, it will weaken the van der Waals forces that exist. Okay, and then lastly, less energy will be needed to overcome the weaker van der Waals forces. Okay, so now let's look at one example. Okay, so here I have two alkane, I have pentane and 2-methyl butane. So if you look closely at these two alkane, okay, both have 5 carbon. So we have over here C5H12. Okay, so let me just write down. So C5H12. So the molecular mass is the same. So that's why we cannot use the effect of molecular size for this one. Okay, because we have an isomeric alkane over here. 2-methyl butane is a chain isomer to pentane. And if you look closely at the boiling point of pentane is higher than the boiling point of butane, even though it has the same molecular weight. Why? Because of the branching over here. Because there exists a methyl group over here. Okay. So, in a graphical method, not a graphical method, I mean a diagram. Okay. This is how it looks like when we have a straight chain alkane with the one that have branch. Okay. The structure over here is more less compact. Okay. And this one is like, if you can look here, it's slightly spherical. Okay. So, what happened? The surface for the van der Waals forces inside 2-methyl butane will decrease. So let's look at the explanation. So 2-methyl butane has same molecular size with pentane. So you need to mention that first. Okay, because we want to remove the factor of molecular size. Then the presence of branching in 2-methyl butane will decrease its surface area. Thus, it will weaken the van der Waals forces exist between the molecules. So, this statement refers to 2-methyl butane. So, less energy is needed to overcome the forces, the van der Waals forces. So, therefore, it has a lower boiling point than pentane. Or, you can say 2-methyl butane has lower boiling point than pentane. So, from what we have discussed just now, when we have alkanes that have the same molecular formula, meaning it has the same weight, the one with more branch will have lower boiling point because the surface area is smaller. But we need to keep something in mind. So here, the boiling point of branch alkane is higher than straight chain alkane if the number of carbon is greater. Okay, so for example, here I have butane and 2,2-dimethyl propane. So by right, in one glance, this alkane 2,2-dimethyl propane has more branch. So we're going to think that 2,2-dimethylpropane will have the lower boiling point due to the branching. But you need to look closer. Okay, because butane only have 4 carbon while 2,2-dimethylpropane has 5 carbon. The molar mass or the molecular weight for butane, it will be 58, so I write down over here, 58 gram per mole, while for 2,2-dimethylpropane, which has 5 carbon, so this is actually C5H12, on the butane is C4H10. Okay, molar mass of 2,2-dimethylpropane is 72 gram per mole. So as you can see over here, we have significant difference between its molecular mass. So instead of focusing on the effect of branching, the boiling point of these two alkanes is differentiated by its molar mass. So that's why as long as we have a greater number of carbon, automatically it will have a higher boiling point, even though it has a lot of branching. The third factor that can affect the boiling point of alkane if we compare a straight chain alkane with a cycloalkane. So when comparing at the same number of carbon, okay, meaning the straight chain and the cycloalkane has the same number of carbon, cycloalkanes has slightly higher boiling points than our straight chain alkane. Okay, so for example, I have here pentane and cyclopentane. Okay, so the molecular formula, if I write down the molecular formula over here, for cyclopentane it's C5H12, and then for pentane C5H12, cyclopentane is C5H10. Okay, so let me write down the molar mass as well. So for pentane, it will be 72 gram per mole. Okay, and cyclopentane will be 70 gram per mole. Okay, so as we can see over here, the mass of pentane is slightly higher by 2 grams per mole because it has extra 2 hydrogens. So by right, the boiling point of pentane should be higher than cyclopentane. But when we do the experiment, okay, when we boil pentane and cyclopentane, what you can see over here is the boiling point of pentane is lower, while the boiling point of cyclopentane is higher. What's the reason behind the difference in the boiling point of the straight chain alkane and cycloalkane? Okay, so this is the reason. So cycloalkanes in planar structure, so it will has a larger surface area and stronger van der Waals forces. Therefore, it will have a higher boiling point compared to the straight chain alkanes. So that will be the reason on why the cyclic structure has a higher boiling point. It's all about the surface area and the van der Waals forces, the strength of the van der Waals forces. So in conclusion, when you have a bigger surface area, so you will have a stronger van der Waals forces, so more energy needed to overcome the van der Waals forces between the molecules. Thus, it will have a higher boiling and also melting point. So now, let's discuss on the solubility of alkanes. Now, before we look on solubility of alkanes, let's discuss about solubility in general. So for solubility, we are going to compare the solubility first in polar solvent. We have polar solvent over here. Okay, and then we're going to look on the solubility in organic solvent. Okay, how to differentiate between these two solvents? I mean, what kind of compound can dissolve in a polar solvent and what kind of compound that can dissolve in an organic solvent. So if it's a polar solvent, the most frequent polar solvent that we're going to use is H2O, water. Okay, so compound that can dissolve in water, it must be a polar molecule. Okay, because when a polar molecule, okay, it meets water, which is also a polar substance, so there will be attractive force between the two substances, between the organic compound and also the water molecule. Okay, once there is attraction between those two, so that's why you can have, you can see that your compound is soluble in polar solvent, in water. Okay, how about organic solvent? So organic solvent, example of organic solvent, okay, example is CCl4. So CCl4 over here is a non-polar molecule. Okay, so the substance or the compound that can dissolve in an organic solvent must be also non-polar molecule. Okay, so in other words, solubility depends on the type of the intermolecular forces. Polar molecule will dissolve in polar solvent. Non-polar molecules will dissolve in organic solvent, which is a non-polar molecule as well, because they can make interaction with each other. The non-polar molecule with the non-polar solvent, there will be van der Waals forces. For polar molecule, the polar molecule can have attraction, okay, polar attraction with the water, that also a polar molecule. Now, let's look on solubility of alkanes. So alkanes are insoluble in water, okay, because water is a polar solvent. So alkane has very low polarity and unable to form hydrogen bonds with water molecule. So as you know, our water molecule H, okay, so this is your water molecule. Okay, we have hydrogens bonded to oxygen, one of the most electronegative atoms. Okay, so it can form hydrogen bond. So if your substance can form hydrogen bonds with water, so it can dissolve it in water. Okay, it is soluble in water. But if there is no hydrogen bond in your substance, for example, our alkanes over here, alkane is a non-polar molecule. So of course, automatically, it does not have any hydrogen bonding, okay, between the molecules. So it cannot form hydrogen bonds with water. So that's why it is insoluble in water. So alkanes are soluble in organic solvent of low polarity. Okay, example of organic solvent: benzene, chloroform, CCl4 and other hydrocarbons. Why? Because, like I mentioned before, in our organic solvent, okay, organic solvent made up of a non-polar molecule. So non-polar molecule will have van der Waals forces. Okay, to be specific, here is our London forces. So the forces is the same with our alkanes over here. So since the intermolecular force is the same, so alkanes can form van der Waals forces with the solvent, with the organic solvent. So that's why alkanes are soluble in organic solvent. So in conclusion, in this video, what we have learned is about the boiling point of alkane that is affected by the molecular size, the factors of branching, and also straight chain versus cycloalkane. And lastly, the solubility of alkane, which is affected by the type of solvent. So alkane is insoluble in polar solvent because the difference in polarity. But alkane can dissolve or soluble in an organic solvent because it can form van der Waals forces with the solvent. So, thank you for listening attentively. That's all.